What else can we got? We did inverse cosine, inverse sine, inverse tangent, inverse sine. Those are the two biggies. We haven't talked about quotient rule. So let's say h of x is 8 minus cosecant of 4x all over x to the pi minus 3e to the x. What does the quotient rule say? And some people are screwing this up. Okay, it's bottom derivative of top minus top derivative of the bottom. How about this? You start with the derivative of the top. You take the derivative of the top first, and derivative of 8 is nothing. Derivative of negative cosecant. Wait, let's see. Negative, the cos are like the negative of the non-cos. So the derivative of secant was secant tangent. The derivative of cosecant is negative cosecant cotangent. And you get the 4x and the 4x, and then times the 4. Oof. Anyway, that is the derivative of the whole top. So we have bottom times the derivative of the top. Here's the bottom. So bottom times the derivative of the top minus the top, 8 minus cosecant of 4x times the derivative of bottom, x to the pi. That is just x to a constant. You put the constant, multiply the constant in front, x to the pi minus 1. And minus the derivative of 3e to the x is 3e to the x. So what have we had? We have bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. What's that you say? This is hideous and ugly? I'm inclined to agree with you. I'm also inclined to think that we can leave this the way it is. Okay, what? The two negatives can make a positive. We could put the 4 in front. What is this? 4 cosecant of 4x cotangent of 4x times x to the pi minus 3e to the x minus, but I'm not seeing any good simplification on this. 8 minus cosecant of 4x times pi x, and I'm off the edge. No, times that all over. Oh, squared! Squared. That's pretty much it. So, yeah, remember your quotient rule. And to finish this little lesson off, I want to talk about 3 different functions. If we had, what do we have? We could have y equals x squared. We could y equals 2 to the x. And y equals x to the x. First one's easy. dy dx is 2x and we're done. 2 to the x is more difficult. It's more like e to the x. The way I would solve this one is I would take the natural log of both sides. Then I can take that x in front. Natural log of y is x times the natural log of 2. And then I would take the derivative of both sides with respect to x. And the derivative, okay, natural log of something is 1 over the something times the derivative of what's inside. The derivative of y with respect to x is called dy dx, and that dy dx is what we're looking for. Now this one's pretty easy actually, because the natural log of 2, natural log is a function and 2 is a constant. It's some number. I would need a calculator to find out what it is exactly, but it's not a crazy number. So this is a constant times x, like 3x or 8x. Derivative of 8x is 8. The derivative of 3x is 3. The derivative of natural log of 2 times x is natural log of 2. And so what we get is we get dy dx is natural log of 2 times y, if you cross multiply the y up, and the y, as we said, was 2 to the x, so it is natural log of 2 times 2 to the x. That's That's not a minus, that's a 2. That's a times. Times 2 to the x. So this is very similar to e to the x. The derivative of e to the x is e to the x. The derivative of 3 to the x, 2 to the x, is 2 to the x times the natural log of 2. Let's do this last one all by itself. Same sort of thing. We didn't do this last semester. Shame on me, but hey, it's never too late. X to the x. Take the natural log of both sides. Natural log of y is natural log of x to the x. You can bring that exponent in front. Natural log of y is x times the natural log of x. And now we can take the derivative with respect to x of everything. We get 1 over y, the derivative of natural log of something is 1 over the something, times the derivative of what's inside, which is the dy dx that we want, is now on the right. We have to use the product rule. The derivative of the first one is 1 times the natural log of x left alone, plus the x left alone. Derivative of the natural log of x is 1 over x. Well, this cleans up rather nicely. We get 1 over y dy dx is natural log of x plus 1, because those x's cancel out. And when you multiply the y up, you get dy dx is, let's say, 1 plus ln of x times y. And y is x to the x, so it's 1 plus ln of x times x to the x. A little bit crazy. This thing is called logarithmic differentiation. That is taking the logarithm of something before you take the derivative of it. And it's generally the trick for when you have a variable for an exponent. It's really hard to just do that right away. I mean, you could memorize the answer for this sort of thing. You'd be like, oh, the derivative of x to the x, isn't that 1 plus natural log of x times x to the x? And that's the way engineers work. And if you are an engineer, if you do work with derivatives all the time, they have huge books like the size of a dictionary or an encyclopedia just full of functions and their derivatives. I'm not quite sure how they get you to look it up. I mean, where in the alphabet would you look for x to the x, you know? And if you looked in the x's, I'm sure you're going to find a lot of stuff in the x's in one of those books. There's also computer programs that do this sort of thing. Some people look down on the way I teach calculus because I don't just teach you how to use a computer that does all these things for you. But I just think that it's not that hard to learn a piece of software. It's a little bit harder to learn how to figure these things out on your own. You who have learned how to do these things on your own will be able to pick up the software a whole lot easier than someone who's learned to do everything with software will go about figuring things out on their own. And so in class I hope to practice this and hopefully catch all those of you who are doing the quotient rule wrong once and for all. Those of you, and I think I'll throw in a logarithmic differentiation just for the fun of it.